Hello, my name is Eric Clausen, and I'm the author of the book, The Topographic Map Mystery, Geology's Unrecognized Paradigm Problem. And this is the fourth lecture in a series of lectures about my book. And the topic of this lecture is what solving the topographic map mystery could mean, especially for the geology research community. And what as I said, this is the fourth in a series of lectures, and this lecture is a standalone lecture, so you don't need to have heard the other lectures to understand this lecture. But I do want to comment briefly on some of the topics that I discussed in the previous lectures, so you know what the background is. In the first lecture, I discussed scientific paradigms, and scientific paradigms are the framework of ideas that define a scientific paradigm and enable a scientific discipline to communicate with each other, the members of a scientific community to communicate with each other and to build on each other's work. So a scientific paradigm is very important to the scientific discipline that's using that paradigm. Scientific paradigms, though, have the characteristic that they enable members who look closely to identify evidence that the paradigm does not explain, and that is referred to as anomalous evidence. And in the case of the geology paradigm, the topographic map, drainage system, and erosional landform evidence, almost all of it is anomalous evidence that the accepted geology paradigm has not been able to explain. Geologists gave up trying to explain it many years ago and have been ignoring the evidence ever since. So the topographic map mystery that I've been talking about is the mystery of what the topographic map, drainage system, and erosional landform evidence is saying, because the geology research community has no clue what that map evidence is trying to say. In the second lecture, I discussed how the paradigm problem developed, and I discussed some of the geologists who in the late 19th century and early 20th century to, basically started the problem. And one of them, William Morris Davis, was primarily the first to start ignoring the topographic map evidence. Thomas C. Chamberlain was very important in developing the concept that there were multiple glacial, interglacial cycles in North America. Douglas Johnson promoted Davis's work. Arthur Strehler tried very hard to find ways to explain Pennsylvania water gaps, and he couldn't. And then I also discussed a J. Harlan Brett's hypothesis about the channeled scablands in eastern Washington state, where Brett's proposed a way to explain the channeled scablands that did not fit the accepted paradigm, and which, as a result, the geological research community rejected. Um, and although today, after some modifications to the paradigm and also some modifications to what Brett's had proposed, the Brett's idea is pretty well accepted. The third lecture, I started out by very briefly discussing some past geology paradigm changes. The geology paradigm has changed several times in the last 200, 300 years, very significantly. And then I turned to my research, which began with a search for topographic map evidence in southwest North Dakota, where I was looking for ice seat marginal floods. And that search eventually led me to a study of Rocky Mountain topographic map evidence. And finally, to a systematic study of detailed topographic maps for the entire Missouri River drainage basin and several adjacent drainage basins, where I was trying to determine how every drainage divide in those drainage basins developed. And that was a study that I don't think anybody had ever done before. And it was an eye opener to me because it was like seeing a totally new planet that nobody had ever seen before. Uh, and what I want to do now is turn to what I found in that study, and which was totally alien to what the accepted paradigm was says and what I had been trained to believe. And contrary to the accepted paradigm, the north-oriented Missouri River tributary valleys, like the Little Missouri River Valley, which in the accepted paradigm are pre-glacial valleys, that what I was finding was that that valley and the valleys, similar valleys, north-oriented valleys, had eroded headward from an ice sheet location across large southeast-oriented meltwater floods. And that was something that, from the accepted paradigm interpretation, is just contrary. It's totally unacceptable from the accepted paradigm viewpoint. And then also unacceptable from the accepted paradigm viewpoint, I found that huge meltwater floods, probably meltwater floods, had flowed across the entire Missouri River drainage basin, and that all valleys in the Missouri River drainage basin, regardless of their size, assuming they were large enough to show up on the maps, and regardless of their elevation, appeared to have been eroded headward across or along these immense floods. And I could even identify sequences in which they had eroded, and these sequences generally progressed from the southeast to the northwest. And again, the accepted paradigm does not see continental ice sheet meltwater getting to most areas in the Missouri Basin, especially the higher elevation areas. Also, contrary to the accepted paradigm, I saw that massive south and southeast-oriented meltwater floods had flowed across and along the east-west continental divide, which just was an eye-opener to me, and then across what are today some of the highest Rocky Mountain regions. And so this is something that from the accepted paradigm is totally impossible. And then contrary to the accepted paradigm, I saw that mountain ranges and entire regions had been uplifted as the large south and southeast oriented floods flowed across them, and that those uplifts blocked and diverted the floodwaters, forcing the floodwaters to go in different directions. So these were some of the key findings that I found in that Missouri River Drainage Basin project that I did. And as I mentioned in the third lecture, that study took me 3 years. And then because I couldn't get anybody to publish it, I had to repeat the study to put so I could put my notes in blog format on the internet, so that when I would present papers to a journal for publication, I could point them to my notes and show them that I had actually done the study. Well, with that introduction, let's look at what I found. And one of the things that I found was that there was a thick ice sheet that had created a deep hole. And what I saw as evidence for the deep hole is what the accepted paradigm sees as evidence for pre-glacial drainage systems. Now, this is the Missouri River, northern Missouri River drainage basin here in Montana, Wyoming, North and South Dakota. And that you'll notice that the Missouri River is an asymmetrical drainage basin here. There's a north-oriented Missouri River headwaters, and then there are a lot of north-oriented tributaries here. And that I found that I could explain the headward erosion of these north-oriented tributary valleys like the Little Missouri Valley here from an ice sheet location, because the evidence that I was seeing on the topographic maps indicated this valley had eroded headward across large floods. The way I could explain this was that if the ice sheet had been located in a deep hole, probably a deep hole that the ice sheet had created, probably with its weight, perhaps by deep erosion, and the weight of the ice sheet was causing uplift of the surrounding area because, as I mentioned, there was evidence that the surrounding area had been uplifted as immense floods had flowed across them. And so my question then became, where was the big hole rim or the deep hole rim? Well, I finally concluded that the deep hole rim is along the east-west continental divide coming down from Canada into Montana and then across Wyoming and into Colorado and possibly into northern New Mexico. And I also found the deep hole rim was located along the Ohio River Atlantic Ocean basin and also the Ohio River Gulf of Mexico basin drainage divide here. Now, I've shown the Arkansas River here because I'm not quite certain whether the deep hole rim was somewhere in the Arkansas River drainage basin or along the southern margin of the Arkansas River drainage basin that I see here, that I've shown here. But in any case, the effect of the deep hole rim was to force meltwater in this central part of North America that was coming from the ice sheet. And the dashed blue line here is showing the approximate margin of the ice sheet, that the meltwater was being forced by the uplift of the deep hole rim on both sides here to flow towards what eventually became the only outlet from the deep hole, at least in the south. Now, there may have been other outlets in the northeast here when you get east of the Ohio River drainage basin area, and there were certainly other outlets in the northwest here to the west of the east-west continental divide. And I haven't done as much research there as needs to be done. Now, this deep hole rim concept, the uplift of the deep hole rim, explained to me why the Rocky Mountains are high today. And the accepted paradigm has a great difficulty explaining why mountain ranges such as the Rocky Mountains, which are not located along plate boundaries, are high. And one of the hypotheses that in the accepted paradigm has been proposed is that the Rocky Mountain region is high because the North American plate has overridden another plate. Although not all geologists are convinced of that, and other possibilities have been suggested. Well, the uplift due to continental ice sheet weight, especially when I was seeing evidence that meltwater floods were flowing across this entire region, made sense, and it probably solves the problem, although it doesn't fit the accepted paradigm. So it probably will be a long time before it's accepted. And also, the development of the deep hole rim probably explains why the Appalachian Mountains in the east are high. That this is a problem that geologists have. The Appalachian Mountains are interpreted to have been formed along a late Paleozoic plate boundary when two continents collided. But most geologists believe that that occurred so long ago that erosion should have reduced the Appalachian Mountains to an almost featureless plain by this time. And they can't explain why the Appalachian Mountains have their present day elevation. But again, ice sheet related uplift probably can solve the problem. But again, it doesn't fit the accepted paradigm. And the problem both here and in the Rocky Mountains is that the ice sheets didn't, according to the accepted paradigm, there's a time problem here that the Appalachian Mountains and the Rocky Mountains are assumed in the accepted paradigm to have achieved their present elevations before the ice sheets developed. Or maybe they didn't achieve exactly their present day elevation, but they had achieved a significant percentage of their present day elevations before there were any ice sheets. Now, how could a thick ice sheet create a deep hole? Well, I think it's important to recognize what geologists using accepted paradigm rules think a North American ice sheet might have looked like. And they don't know, and I don't know either. But so there have been reconstructions. This diagram illustrates two reconstructions, one where it was fairly thick. The white area is showing that the ice sheet, this is for the North American ice sheet, where the ice sheet was more than 3 kilometers thick, this area more than 2 kilometers thick, this area more than 1 kilometer thick. Over here, this is a thinner ice sheet model that's been constructed. And again, the white areas is assumed to have been more than 3 kilometers thick. This area, 2 kilometers thick and 1 kilometer thick here. So, and then this would be less than 1 kilometer thick along some of the edges. Well, either model, the amount of ice involved would have had a tremendous weight. And I'm inclined to think that the deep hole was created by an ice sheet at least this thick. So this is standing at least 3 kilometers high, maybe even an ice sheet that stood even as much as 4 or 5 kilometers high. But in any case, the weight of the ice sheet would have caused the surrounding areas, including mountain ranges, to rise so as to create the deep hole rim, and that this uplift of the deep hole rim would have occurred as meltwater from the ice sheet margin was flowing across the rim, and eventually the uplift of the deep hole rim would force the meltwater to flow in other directions towards what eventually became the deep hole's only southern exit. And that the concept that an ice sheet would cause subsidence is well established in the accepted paradigm. And there's good evidence if you go up into northern Canada or any area that's been glaciated where it's been documented that the land is rebounding from having been having been under an ice sheet's weight. The one thing that this diagram doesn't show, and that doesn't show up in most of the accepted paradigm literature, is that as this subsidence occurred, there was uplift in surrounding areas. And that's what the topographic map evidence is telling me. It's saying that as the weight of the ice sheet caused subsidence under the ice sheet, that there was uplift occurring in the surrounding areas. So And again, the problem is in the accepted paradigm, much of that uplift is assumed to have occurred prior to the ice sheets. So that's why the accepted paradigm doesn't see that uplift. Now, the topographic map evidence and the erosional landforms also um, provided me some clues about how the thick ice sheet had melted. And I want to start out and say that the topographic map evidence, after I started to be able to explain it, seemed to described two linked ice sheets. First was a thick ice sheet that created the deep hole, and second, there was a linked second ice sheet that formed on the deep hole floor around decaying first ice sheet remnants. And let me show you some of the evidence that led me to that conclusion. And again, remember that the thick ice sheet margin is shown by the dashed blue line here. And we're going to be talking about the areas within the ice sheet now, looking at how the ice sheet might have melted. And here, these are two maps of that I put side by side. These maps are showing elevations with this is in the northern state, this is North Dakota, and this is South Dakota immediately below it. Unfortunately, the elevations use different colors in the two states, although the maps are otherwise adjacent to each other and the features are adjacent. This is the Missouri River here, and you can see the Missouri River continues here. This is the Black Hills in South Dakota. These are the Turtle Mountains in North Dakota. And the feature that I want to show you here is the Missouri Escarpment here, which is a very prominent step from low plains to high plains, and it extends across North Dakota. And I'll show you in the next slide that it actually extends across Saskatchewan into Alberta. So it's a huge linear feature, and it comes down like this into south central South Dakota. These are the Turtle Mountains, and they're bounded by an escarpment very similar to the Missouri Escarpment. And the cap and the elevations on the Turtle Mountains are very similar to the elevations on this side of the Missouri Escarpment. And as I mentioned in the third lecture, the Missouri Escarpment is a step of about 100 to 200 meters or 300 to maybe 600 feet. In some places, it's quite noticeable. In other places, it's you hardly notice it when you go up it, although you're definitely climbing elevation when you go up it. And so that we've got escarpments on both sides here. And then when we come down here into South Dakota, what we're looking at here is an escarpment surrounded upland known as the Prairie Coteau. And I'm going to show you a topographic map of this area, and I'll show you a topographic map of this area, and also a geologic map showing the glacial deposits of this area before we get done. But in any case, there is escarpment surrounded lowland between the Prairie Coteau and the Missouri Escarpment in South Dakota. And there's an escarpment surrounded lowland between the Turtle Mountains and the upland to the south and west of the Missouri Escarpment. And I interpret these escarpments to be the walls of what were ice-walled and bedrock-floored canyons that had been sliced into the thick ice sheet as it was decaying by huge supraglacial meltwater rivers that just sliced into the ice sheet and eventually sliced down into the bedrock underneath. And these are routes that the huge meltwater floods used. And this one emptied into south central South Dakota, and downstream from this, the Missouri River Valley is much larger and wider than it is upstream from it. So there's good evidence that something caused much more water in the Missouri River Valley downstream from where this emptied than it than upstream from it. In any case, that these escarpments in the accepted paradigm are assumed to be preglacial escarpments usually, although in the accepted paradigm, it's quite legitimate to assume that the ice sheets did modify the escarpment and maybe streamlined them some. But anyways, this was a totally different interpretation of these escarpments. And from the accepted paradigm viewpoint, these when and how these escarpments were formed is not well understood. In the interpretation that I have, that the ice-walled and bedrock-floored canyon interpretation, the origin is quite well explained, and these are remnants which are helping me define how the thick ice sheet melted. Now, this is looking at Canada, and unfortunately, the maps that show the features, either I've got to get very detailed maps, or the maps don't show the features right. In any case, you can see the Missouri escarpment coming up here through North Dakota, like I showed you, and then across Saskatchewan, roughly along this line here, up into east central Alberta. And that escarpment is approximately 1,000 kilometers long or longer. So it's a major feature that the accepted paradigm has never adequately explained. Excuse me. And there are other isolated escarpments surrounded uplands in southern Saskatchewan and southwestern Manitoba that can be used to identify other ice-walled and bedrock-floored canyon locations. So that there's good evidence in this area to describe how the thick ice sheet melted. Now, to why this was important and what led me to this was that these north-oriented valleys, which I had been mapping and studying, like the Little Missouri Valley here. This is the Black Hills in South Dakota. This is the approximate ice sheet margin here. And this is the Missouri River here. And the dashed red line here is showing the approximate position of the Missouri escarpment. And excuse me, what I was finding that at least some of these valleys seem to be eroding headward, not from the ice sheet margin, but probably from the ice-walled and bedrock-floored canyon that the Missouri escarpment is the south and west wall of, or the remnant of the south and west wall of it. And so, and what I interpreted to be going on as these valleys eroded headward from that ice-walled canyon, they were diverting the meltwater floods back into the ice sheet, into that ice-walled bedrock-floored canyon, and then at first southward to the lower Missouri River, And again, as I explained, to the south of South Dakota, the Missouri River Valley is much larger than it is in South Dakota and North Dakota and Montana. Um, and that eventually, as ice sheet melting progressed and this ice walled and bedrock floored canyon network developed, that new routes opened up, which diverted the flow in the canyon network from the south into to the northeast and eventually to the north. So this was a very important factor here. Um, and that diversion of that meltwater flow from the Gulf of Mexico to the north created a climatic change, which was a very important change. Now, remember, as those, I'm going to go back to that slide again, as these north-oriented valleys eroded headward, they were also creating the north-oriented drainage system that we have today, leading into the Missouri, that leads into the Missouri River. Now, at this time, there was no Missouri River. So all of this drainage was going into the ice sheet location and into the ice-walled bedrock-floored canyon network. And as a result, the ice sheet was picking up a lot of the drainage from what was now the uplifted area in Wyoming and Montana and even South Dakota that had that the floods had been flowing across, because each of these valleys moved the floodwaters in here, and the floodwaters no longer drained the area to the south and east of this. But anyways, we now have a major north-oriented drainage system feeding into the ice sheet floor. And what happens when that north-oriented drainage system is first feeding into the ice sheet floor and then being diverted back into back south to the Gulf of Mexico, which you can see here. And that as huge volumes of meltwater flow into the Gulf of Mexico, that's pushing warm water out of the Gulf of Mexico into the Atlantic Ocean. And that's setting up warm water currents that are going up here, and that's creating a climatic condition that is resulting in the melting of the thick ice sheet. But when the south-oriented meltwater floods are diverted into the north, into the Hudson Bay and the Hudson Straits area in the North Atlantic, that the situation is reversed. No longer is warm water being pushed out into the Atlantic Ocean from the Gulf of Mexico, but instead cold water is being pushed down from this area into the Atlantic Ocean. And that has the effect of eventually cooling the climate and creating essentially an ice age. And now we have all this north-oriented water flowing into the deep hole, both in the Missouri River drainage basin and the Ohio River drainage basin. And this water is, it's now cold up here, and we still have thick ice sheet remnants. So this water is filling up the deep hole floor around the thick ice sheet remnants, and it's freezing. And this is creating the second linked ice sheet that I talked about. And this ice age probably also caused the alpine glaciers in the Rocky Mountains and other high uplifted mountains that the weight of the ice sheet had caused, the thick ice sheet had caused to be uplifted. Now, looking at some evidence why uh, that I think there were two types of ice sheet, um, and that this is the northern tip of the Prairie Coteau escarpment that I showed you before. This is along the North Dakota, South Dakota border. This is the line here. And this is the west-facing escarpment along the Missouri Coteau. This is the east-facing escarpment. And that many geologists would assume that ice sheets flowed around this, and that helped streamline this feature. But if you look at the upper area here, which is known as the Prairie Coteau upland surface, it's a very hummocky topography, lots of little lakes and ponds. And this is typical of what glacial geologists consider to be an area where an ice sheet slowly melted out and deposited material. In other words, this was where an ice sheet stagnated. Now, if you look at the landscape on either side here, you don't see that type of topography. And the glacial deposits on either side here are more typical of what you would find if the ice sheet had been had a very wet base and had been flowing on that wet base, and had been moving at least rapidly for an ice sheet. So that this is what we would call this, and the ice sheet here seems to have been quite mobile. And this is where I assume the meltwater and drainage from the north was accumulated and then froze probably from the top down around a decaying thick ice sheet remnant. Now, if we proceed up into North Dakota, this is the Turtle Mountains here. Here's the escarpment surrounding the Turtle Mountains. This is the Missouri escarpment here. This is the Missouri Coteau area, which is an area, it's also a very hummocky topography area, lots of little lakes and ponds, at least when it's not real dry. And that this is an area where an ice sheet stagnated, and the Turtle Mountains has the same type of topography, lots of little lakes and ponds, and an ice sheet. It's all the characteristics of a stagnant ice sheet up there. And then this area in between, where I think which was the floor of the ice-walled and bedrock floored canyon, is characterized largely by glacial deposits indicating a wet-based, very mobile ice sheet that was present here. So this is some of the evidence that I'm using to interpret the fact that a second ice sheet formed around remnants of the first ice sheet. And there's further evidence. This is a preliminary map of glacial deposits in North Dakota, looking at the same area that I showed you in the last slide. This is the Missouri Coteau area. The Missouri escarpment runs right along here. And this is the Turtle Mountains here, and there's the escarpment surrounding the Turtle Mountains goes like this. And you can see they've shown with the dark brown band here where they interpreted the stagnant ice sheet to have been. Some maps show it to have extended further to the south and west of what you see here. This is the Missouri River that you're seeing going here. In any case, this is more evidence supporting the concept that there was a thin ice sheet that formed around remnants of the thick ice sheet. And so there's both topographic map evidence and geologic map evidence supporting this. Now, I'm going to, the rest of the lecture, I'm going to compare what I found on the topographic map and with what the accepted paradigm says, because the topographic map, drainage system, and erosional landform evidence essentially described a fundamentally different geology and glacial history paradigm that I'm going to call the new paradigm, and from the accepted paradigm that the geology research community uses. And I'll use the word accepted paradigm for that. Now, these two paradigms are incommensurable, which means there's no common standard by which the two paradigms can be compared. And I can assure you that geologists trained in the accepted paradigm have a very difficult time understanding me when I talk about the new paradigm. In fact, they tell me that I'm crazy and I'm talking about things that are impossible. Um, but Thomas Kuhn, who wrote The Structure of Scientific Revolutions, in which he describes how paradigms change, um, he suggests that the only way a scientific community can determine which of two incremental paradigms is the best to use is to determine which of the two paradigms best explains the evidence and opens up the most new research opportunities. He says there's no way to determine if a paradigm is correct or incorrect. And it's quite possible that both paradigms are incorrect and that there's still a third paradigm out there that is even much better. But in any case, the only way to determine which of these two paradigms is best is to determine which one best explains the evidence and opens up the most new research opportunities. And that in research opportunities, at least in the short term, are probably related to funding opportunities. And there's no question that the accepted paradigm has better funding opportunities than the new paradigm. But in the long term, that may not always be the case. Now, what evidence does each of the two competing paradigms in this case explain? The new paradigm, as I've explained in the previous lecture, and it successfully explained most of the Mississippi River drainage basin topographic map evidence, drainage system, and erosional landform evidence, although I still have unresolved questions about some of the topographic map evidence in the Great Lakes and New England area. The new paradigm may explain evidence on other continents. I have looked at other continents, but I have not studied them in detail, and much further research is needed as to whether the new paradigm can explain evidence on other continents. The accepted paradigm appears to have successfully explained an awful lot of sedimentary rock, fossil, and other types of evidence, but it has almost completely ignored the well-mapped drainage system and erosional landform evidence because geologists, at least to date, have been unable to explain that evidence. However, I want to say that a close reading of the geology literature suggests that the accepted paradigm has many serious problems when trying to explain other types of evidence. So the accepted paradigm is not always leading geologists to clean explanations of the evidence that it is explaining. Now, how does each paradigm explain North American glaciation? The new paradigm, as I mentioned, sees a thick ice sheet that created a deep hole forming first, and then as that ice sheet created, a second, much thinner ice sheet formed on the deep hole floor. And that the second ice sheet was created when meltwater floods and other drainage were diverted from flowing south to the Gulf of Mexico to flowing north across the deep hole floor to reach northern oceans, and that caused a climatic change which froze the north-oriented water around the decaying first ice sheet remnants and which created an ice age. The accepted paradigm sees multiple continental ice sheets forming and then melting, probably at regular intervals, governed by astronomical um, events, and that this occurred during the last 2.6 or so million years. And they see no evidence for a deep hole in the North American continent, at least a deep hole created by an ice sheet. And the last accepted paradigm ice sheet, which is the Wisconsin ice sheet, may correspond with the new paradigm's second thin ice sheet. I don't think there's anything in the accepted paradigm that corresponds with the new paradigm's thick ice sheet. Now, how does each paradigm see North American drainage system development? The new paradigm sees almost all North American drainage systems to have developed by headward erosion of valleys across and or along massive first ice sheet meltwater floods, and that except the Missouri and Ohio rivers were developed along as ice sheet marginal rivers along the margin of the second thin ice sheet's margin, not along the first ice sheet margin. And the new paradigm sees no evidence for what the North American pre-glacial drainage system looked like. Now, the accepted paradigm is built on the assumption that much of the North American drainage system to the south of glaciated areas developed prior to the ice sheets, and that there are abandoned pre-glacial drainage system valleys that can be traced across glaciated areas in Canada, and that the Missouri and Ohio rivers blocked the drainage that used to flow in those valleys. Now, how does each paradigm explain Rocky Mountain and Appalachian Mountain uplift? The new paradigm sees Rocky Mountain and adjacent area and Appalachian Mountain uplift as being related to the weight of a thick continental ice sheet that created its deep hole, and that the deep hole rim was rising while massive south-oriented floods first flowed across the rising deep hole rim and were later forced by deep hole rim uplift to flow towards the deep hole's only remaining southern outlet. Now, the present day Rocky Mountain and Appalachian Mountain elevations in the accepted paradigm are unresolved problems. And though some geologists, as I mentioned, believe the Rocky Mountain elevations may be because the North American plate has overridden another plate, the accepted paradigm does not see a relationship between the mountain uplifts and the continental ice sheets. Now, how does each paradigm explain United States middle and late Cenozoic sediments? The new paradigm considers massive and prolonged first ice sheet meltwater floods to have flowed through what were temperate and warm climatic zones. In fact, it assumes that the thick ice sheet had flowed south into temperate and warm climatic zones, and that was what was causing the thick ice sheet to melt. And that as a result, the meltwater floods transported and deposited most of the what are now United States middle and late Cenozoic sediments. And these floods probably forced very rapid mammalian evolution by periodically wiping out regional populations, which then had to be reestablished. Now, the accepted paradigm, on the other hand, sees all of the pre-Quaternary middle and late Cenozoic sediments to have been transported and deposited under conditions similar to conditions that we see today, although there may have been major volcanic eruptions that were producing large quantities of wind-blown volcanic ash. And this interpretation requires long periods of absolute time to explain mammalian evolution. And so that there's a very big difference between the accepted and the new paradigms in this regard. How does each paradigm explain United States middle and late Cenozoic climatic conditions? The new paradigm sees that snowfall continued to feed a middle and late Cenozoic thick ice sheet that stood higher than most of today's highest mountain ranges and which had flowed southward into temperate and maybe even warm climatic regions. And as a result, there was a massive melting occurring each year along the ice sheet margin. And the thick ice sheet did not create ice age type conditions except on its high elevation surface. To the south of the ice sheet, conditions were quite temperate and warm. The accepted paradigm, on the other hand, sees ice age type climates existing whenever a late Cenozoic ice sheet developed, with warmer conditions developing during the interglacial periods between the continental ice sheet. And they use fossil evidence to document warmer climates existed during much of the preglacial middle and late Cenozoic time. So again, there's a big difference here. How does each paradigm explain Cenozoic time? The new paradigm is these thick ice sheet the thick ice sheet existed for much of middle and late Cenozoic time, and the second ice sheet melted probably about the same time that the accepted paradigm sees the Wisconsin ice sheet melting. And as a result, the new paradigm does not need as much middle or late Cenozoic absolute time as the accepted paradigm needs, although there's no way to use the topographic map evidence that I've been using to determine absolute age dates. So I can't really say anything about absolute time. Other than I can say that the new paradigm doesn't need as much time in the Cenozoic as the accepted paradigm needs. The accepted paradigm sees ice sheets existing only during the last 2.6 million years or so of the Cenozoic, and during the 40 to 50 million years previous, which would be the middle and late Cenozoic time, when the thick ice sheet probably existed in the new paradigm. The accepted paradigm doesn't see any ice sheets at all. And the accepted paradigm, I should say, accepted paradigm absolute dates for those middle and late Cenozoic time sediments do not support the new paradigm interpretation, and the new paradigm interpretation does not support the accepted paradigm interpretation absolute dates for those sediments. And I'm going to conclude now with just a couple comments. The scientific paradigms are very difficult to change, and they often only change when a new generation of scientists who are not heavily invested in the old paradigm recognize how the new paradigm explains evidence that the old paradigm could not explain, or that the new paradigm offers research opportunities that the old paradigm did not offer. And finally, historically, geologists have been very slow to adopt fundamentally different new paradigms. And usually when new paradigms have been proposed, that those new paradigms have been initially rejected outright, and that although if the new paradigm really did explain the evidence better, then the old paradigm eventually was phased out and the new paradigm eventually succeeded. But it sometimes took several decades for that to occur. And with that, I'm going to